So, welcome to comp541 Deep Learning. My name is Deniz Yüret, and we'll be spending the semester together. I want to briefly sort of go through some of the administrative details of the class, and then do some sort of demo introduction to deep learning in general. Okay? So, first thing to note is we have a website, and the easiest way to get to this website is courses.ku.edu/comp541, and all the information you will need will be posted on this website. In addition to this website, we're going to also use Google Classroom, which is the third link there, for some of the assignments and labs. The certificate program users are going to use Blackboard, but in this class we're not going to use Blackboard. We have a mailing list, which I indicated with the forum link on the left there. Make sure you're actually a member of the mailing list. Normally you get automatically added when you register for the class, but if you're auditing or if the registrar messed something up, make sure you're in the mailing list so you get the announcements. Plus, the mailing list is the main discussion forum for class-related questions. So please don't email me or the TAs directly, because our mailboxes are usually full. If you have a question about the class or the projects or anything, just send it to the mailing list, and I'll try to get back to you within 24 hours. Okay. The most important part of the course is going to be the semester project. So each one of you is going to pick a paper to work on. If this paper comes from a field that you're interested in, you're doing your thesis in, all the better, more synergy. But we will release a list of papers that you can pick from. These are from the deep learning literature that have been papers that have been published or posted in an archive in the last few years. And you will pick one of these papers and spend the rest of the semester with this paper. You're going to read it, understand it, re-implement it, replicate the results, and hopefully, possibly improve on those results. Okay? And this whole process takes a very long time. So we're going to start early. So that's why one of your first assignments is going to be pick your paper and start reading it. I will send more information about this very soon. In our implementations, when you're replicating this study, or in general in the labs for this class, we're going to use the Julia language, which is a language fairly close to MATLAB in terms of its syntax, but it has a lot of advantages that we're going to go into more detail on. The Julia language can be downloaded from the link over there, and in Julia language we have a package called KNet, which is the Koç University Deep Learning Framework, which gives you some utilities that make it easy to implement deep learning models flexibly. The main textbook of the class is Deep Learning. I think it's available on the at the bookstore. It's also available online. And for the second part of the class, possibly, we're going to do some reinforcement learning, and the main text for that is the Satınam Barto text. The links of both of these are on the main website again. Even though I recommend downloading and installing Julia and KNet on your own laptops and bringing your laptops to the labs, as we advance a little bit, you will see that your laptops will be insufficient to train the models that you want to train, and you will have to learn how to use GPU servers. There are two sources of GPU servers that we can use in this class. One is the Amazon cloud. This AWS link points to the Amazon cloud. So we will send instructions or post instructions on this website on how to sign up for the Amazon cloud. As Koç University students, you should get free $100 credit, and you should be able to find GPU servers to use for 20 cents an hour. So that should be sufficient for you for most of the semester, at least. One thing about Amazon is that when they give you, when they open your account first, they only allow you to log into basic machines. They don't, in order to log into GPU machines, you need to email them for permission. So the sooner you do that, the sooner those machines will be available to you. And if you can get that done by this Friday, you'll be able to practice using these machines in the lab section. The other sources are local high-performance computing center, called, the new name is KUACC now. But that's usually full because of all the research stuff going on, so it will be difficult to find time there, so I highly recommend making use of the Amazon cloud. Let's see if there's any other things I want to. Lab sessions. I don't see any lab sessions for this class yet. Do you guys see it when you look at QSIS? Okay, so there's going to be a lab session on Friday, and we want to start it this Friday, so I wrote to the registrar today, so hopefully before Friday we will have an assigned time in class for the lab session. And this first lab is going to be about Julia, learning Julia. It's going to be a little Julia tutorial, so I highly recommend that you don't miss it, and you go to the lab with Julia installed on your laptops. It's going to take place in a regular classroom, not a computer classroom, so you take your own machines. I mentioned before the project topics will be listed, and the due date for picking your project is Feb 16. That's coming pretty soon. At the end of this class, we're going to hand out a little self-assessment quiz. This is the to sort of see if you have the necessary background to take this course. Necessary background includes practical knowledge of multivariable calculus and linear algebra and probability and statistics, and a good degree of programming. So this is for information purposes only. It's not going to affect your grade, but if you find that you can't do half of the questions in this self-assessment quiz, you may want to reconsider taking this class, maybe retry it after you fix some of the other ones. Okay, so before I start the actual lecture, are there any questions for me? All right. Yeah. Yes, there are office hours, and they are listed in the syllabus. I think mine are Tuesday, Thursday mornings, and the TAs will be also listed in the syllabus shortly. Okay, so let's get started then. I'm going to sort of spend today giving you a small history of where deep learning comes from. The deep learning revolution we're in right now, you may sort of read in popular news articles or follow on Twitter. There's a lot of new things going on, new problems being solved that were either we thought were difficult to solve or impossible to solve until a few years ago. So the last 5 years have been really exciting for AI and machine learning and deep learning in particular. But this is not the first time this is happening. This is actually, I think, the third time this is happening. So I want to take you through the history and show you what happened, what caused the first two revolutions, and what's new in this new third revolution. So people actually realized that there are neurons in the brain at the beginning of the last century. And a biological neuron looks like this. It has a cell body. It takes input from these branches called dendrites, and when it takes enough of the right type of input, it gets excited enough to actually send the electrical pulse along the axon, which is its output, which is corrected to other neurons down the line. So once people realized this is the working of a basic unit in your brain, people got excited about sort of experimenting with computational models of this. This is a very, very simplified computational model of a neuron. It's not very realistic, but it's going to form the basis of a lot of the deep learning models we're going to build this semester. So we represent inputs to a neuron by these X numbers. Each input is going to be multiplied with some weight indicated by the W's. So those W's sort of represent the synaptic connection strengths. You know, not every connection is equally important for a neuron, so W represents the importance of the connection. And in fact, W can be a negative number, which means the connection is not excitatory, it's inhibitory. So the higher that particular X is, the lower the total input going into the cell body. The cell body is going to be represented by a sum of all these weights multiplied by all these inputs, W's and X's summed together, possibly with a bias. And whenever this sum, for example, is positive, then we're going to say our neuron outputs some signal, and whenever it's negative, it doesn't output a signal. And that condition of when to output something and what to output is represented by this activation function f. So this activation function f is some function of the total input that is incoming to the neuron. Okay? So one can actually represent a lot of different functions using a combination of these neurons, artificial neurons. However, it's not trivial how to actually make them learn stuff, how to train them. Okay, so even if we know there is a solution out there, a particular set of weights that solve a particular problem, like recognizing handwritten digits or something, we don't know how to find that. So the first algorithm that basically discovered how to find that was the perceptron algorithm. And that's one reason why these very primitive neurons are called perceptrons. But I'm going to show you a little demo of the things that we can do with these types of neurons. So our first demo is going to be linear regression. You're going to say, what does linear regression have to do with an artificial neuron? Well, in linear regression, we have a bunch of X inputs, and they each have weights. We add them up, and then we output that as the final result of the calculation. So basically, a linear regression corresponds to a neuron with the activation function equal to identity. So perceptrons, linear regression, logistic regression, these models that you may have heard in your previous classes, they all start the same way. They basically all start by calculating a weighted sum of their inputs. So let's do an example of linear regression first. So we're going to download some data and summarize the inputs. Okay, excellent. All right. So this data comes from the UCI machine learning repository, which is an old famous database of different standard problems that machine learning researchers use or used to use. And this particular input is about housing prices in Boston in the 1970s. Okay, so it has an X matrix, data matrix that contain 13 different features for these houses. So for example, the neighborhood, the closeness to roads and business centers and schools, etc. And there's 506 instances, 506 different neighborhoods. The output consists of a single number, 1, and 506 is still the number of instances. And the output is sort of the average house price in that neighborhood. Okay, so and our task is basically to take this data and figure out if we can, given the inputs, if we can predict the housing price. Okay, so to do that, we're going to define some functions. So you don't know Julia yet, so don't worry about it. It's fairly close to pseudocode or math, so we can explain exactly what's going on. So predict is a function. It takes W and X as input. You can think of W and X as matrices of weights and inputs. And W has two components, a vector of array of weights that is to be multiplied with X, and another array that basically includes the biases. Okay? So to keep it easy, you can think of X as a single number, and W has two numbers. The first number multiplies X, and the second number is bias. But if you put vectors or matrices instead of single numbers, this formula still works. Okay? So this is basically the representation of that artificial neuron. I'm multiplying my inputs with a bunch of weights, and then I'm adding a bias. Now, we're going to get into the details of loss functions in a little bit. But basically, once you have your data and you have your model, the third important thing in machine learning is to define an objective function. Right? So what are you trying to optimize? If the model gives you some predictions, how are you going to measure how good or bad those predictions are? And the thing that measures that is called loss or error function. And in this case, I define loss to be a function of W's and X's, my weights and inputs, and also Y's. Y is the correct answers, right? Y are the real prices in the data. So if I use this predict function to calculate what the housing prices are, to predict them from my model, and then take the difference between the real Y's and the predicted Y's, and take the absolute value squares, and take the average. So this is sort of the thing that I want to minimize. The closer the predicted values are to the Y, the smaller this number is going to be. So what I want to do is find the weights, W, that basically minimize this function. Okay? And in order to train this thing, I have to use its gradient. I'm going to talk about that more next week. For now, don't worry about it too much. So these three lines basically define the whole model. So I know, given a W and X, how to predict the Y's, and I know, given predicted Y's and real Y's, how to calculate my loss.
May I ask?
Yes, of course.
Why did you take the absolute value before you squared? Just
no reason, except if Julia has this function, because if these guys are complex numbers, then squaring them and squaring their absolute values may be different, I think. But yeah, this is basically just squaring everything, element-wise. Any other questions? So we're using the mean of the squared differences as our loss function, basically. Okay, so I'm going to initialize the model now. So here's my initialized model weights. So I have two components. Here are the 13 numbers that I'm going to multiply with the 13 input parameters. That's W1. And here is the bias, which is a single number. That's W2. Okay? So what's going to happen is I'm going to get 13 numbers in. My X features. I'm going to take a dot product with this vector, and I'm going to add that. So I just made these numbers up, so I don't expect them to perform very well. So I can actually calculate the loss of this random thing, and the loss happens to be 594, which is, this is the average squared difference between my predictions and the actual predictions, which is pretty bad actually. And I can also calculate the loss gradient. Now, what's a gradient of a function? Anybody remember? So what is the gradient of the loss function? Remember, loss is something that takes W and some other things and calculates a single number called the loss, right? So what's the gradient of that?
Derivative of a vector function.
That's right. So we have a function whose input is a vector, output is a scalar, and we call this derivative of a gradient. And the output of the gradient is basically the same size and shape as the input of the original function. So notice that W had 13 numbers in the first component and a single number in the second component. Gradient of W also has 13 numbers in the first component and 1 number in the second component. And their meanings are as follows. Their meanings are, if I point to any number here, let's say I point to this number, it says minus 6.8, okay? So what this shows me is that in the original function, if I increase this number by epsilon, then the output is going to change by minus 6.8 epsilon, okay? So each of these numbers is basically how sensitive the output is to moving this particular coefficient. Okay, so that's what gradient means. So why is gradient important? Well, my goal is to minimize loss. So in order to minimize loss, I can basically look at these numbers and say, aha, if I increase the first coefficient a little bit, my loss increases, right? Because the coefficient, sensitivity coefficient is 7.5. So I better decrease the first component and increase the second component, and etc., etc. So I can look at the signs and magnitudes of these numbers and decide how to move my weights in order to drive the loss down. So let's make sure we understand these gradients. So what did I do here? So W2, let's look at W2. What was W2? W2 was the bias, 0, right? So, and the sensitivity of the output to the bias was minus 45. So that means if I move the bias epsilon, then the output should move minus 45 epsilon, okay? So to test this theory, I'm going to actually change W2 from 0 to 0.1. Who can tell me what's going to happen to the loss? The original loss was 594.4. What's the resulting loss going to be?
Increase by 0.67.
Increase by 0.67.
Due to
So this is W2 is this, by the way. So this is W1. W1 this is this whole vector.
Increase by 4.5.
Right. So we expect if I increase the bias by 0.1, I expect the output, the loss, to decrease by 45 times 0.1, which is 4.5. So from 594.5 roughly, I expect the loss to become 590-ish. So let's see if that's true, if we interpreted these things correctly. And you see that the loss actually dropped to 590. Okay? So you should basically, if you forgot what a gradient was, please play with these things until you have a feeling of what these numbers actually mean. Okay? So now I'm going to train this particular model using these gradients. This is not the only way to train linear regression. This is actually not even a particularly efficient way to train linear regression. But we're introducing this algorithm called SGD, or stochastic gradient descent, because it's applicable to more complicated models as well. So roughly speaking, I don't want to get into too many details, which we'll do later, but roughly speaking, what this does is it takes the original weights and the data. The data is a bunch of XY pairs. So for each XY pair in the data, it calculates the loss gradient, which we explained earlier. And then it changes each component of W in the negative direction of this loss gradient, trying to drive the loss down. Okay? And this LR is just called the learning rate. It's a small coefficient, because we don't want to take very big steps. If you take very big steps, we might get unstable results. You want to move in that direction slowly. So this LR equals 0.1 causes that. So that's our main training loop. And if I define that, and if I apply this about 10 times, here's the weights that I get during those 10 iterations, and I can calculate the losses for each step, and here's the loss for those 10 iterations. Remember that the original loss was 590, so you can see that the algorithm is driving those down pretty sharp. And if you go too much more, it doesn't actually come down that much. And we can even plot a learning curve with this. Hopefully so. Any questions so far? We're waiting for the plot.
May I ask?
Yeah.
So while training, so for each member of, for each weight, you use the for loop, right? Why
Yes.
don't you just use a vector? So don't you generally want to avoid for loops?
In the training, the for loop was used for the different XY pairs. So for each XY, I calculated a direction to move in, and I moved W in that direction. Are you talking about that
No,
for
not
loop?
that one.
Okay, in the inside for loop is basically W has two components. And the first component is a vector, the second component is a scalar. And that for loop is basically just taking two steps, updating those two components. But there are, in the KNet package that we're going to use, there are functions called update that basically take the whole W and do all of this automatically for you. And here's our graph showing that loss is decreasing by epochs. Epoch means number of times we went through the data set. Okay, so one pass through all the examples in the data set is called one epoch. And we did that 10 times, and we drove the loss from 590 to 20 something. Okay. All right. So now I told you that artificial neuron, basically, if you don't put any F activation functions in front of it, let's go back and look at the artificial neuron. So we're basically building this artificial neuron which calculates this linear thing. And in the case of linear regression, this thing called the activation function is just the identity. Whatever number comes from W's and X's, I basically output that. That's good for regression problems. Regression based, by the way, means your outputs are numerical. But we want to apply these models to also classification problems. Classification means your outputs are not numerical, they're categorical. And if you want to do that, we need to play with the loss function and the output of this model a little bit. Okay? So let's do a classification example. So for my standard classification example, I'm going to use the MNIST dataset. MNIST is like the Drosophila of machine learning. Everybody basically plays with MNIST first. It's a data set of handwritten digits. Let me show you what it looks like. So we're going to load these handwritten digits. There is, and I mini-batched them. We're going to explain that later as well, but basically, in the previous example, we were going through each instance one by one. It turns out, especially if you're using a GPU, that's not a very efficient thing to do, because most of the GPU just remains empty if you do that. So what people do is people mini-batch their data, which means they take, let's say, 60,000 examples, training examples, which is what MNIST has, and they divide it into chunks of 100, okay? And they use 100 examples at a time to do the training. That's called mini-batching. So I have 600 mini-batches of training data and 100 mini-batches of test data in this example. So each mini-batch has 100 instances, so that means I have 60,000 training instances and 10,000 test instances. Let's see some of these instances. What do they look like? Basically, they look like this. They're just pixel arrays. Okay, so there are 28 by 28 grayscale images. So there's 700 something pixels, and we're going to use the values of these pixels. Each pixel value is a number between 0 and 1, or 0 and 255 if you want. And we're going to take all of these 782 or whatever pixels, multiply them with that many weights, and use the exact same calculation we used before to make a prediction. And then we need to convert that prediction into somehow into a prediction about which digit is this picture. Okay, so we have 10 digits, 0 to 9. We want to predict which digit was written. So for that, the predict function is going to be the same, pretty much, as before. So W, there is W. W has two components, the weight matrix and the bias vector again. X's come in, and W1 times X plus W2 is basically the same exact function. This mux function here is only because X is not a matrix. It's a four-dimensional array representing images, so this converts it, does some dimension conversion. It's not important. So W1X plus W2 is still the same. But I will change the dimensionality of W. So what I'm going to do is so in the initial example, my x's were 13-dimensional vectors, and then my w, actually let's call this w, it is x that was also 13-dimensional, and I multiplied them, got a single number for my prediction, and added a bias, and that was my prediction. Okay? So in this case, what I'm going to do is, I have an x that is 782 dimensional, and what I'm going to do is I'm going to have a w that's a little fat, so 782 here, but 10 over here. Okay, so if you want, I have 10 different vectors like this, if you will. And then when I multiply these things, each of these numbers is going to be sort of the dot product of that particular row of w and x, right? And I'm going to use each of these numbers as a score for a particular digit. Okay, so the first number is going to represent the digit 0, the second number is going to represent the digit 1, and I'm going to say whichever digit gets the highest score, that's my prediction. Okay? So that's how I use this, linear machine to do the classification problem. So again, I'm comparing the Y gold, which is the gold answers, and my prediction outputs. But what I'm doing then, I'm feeding this into a function called NLL, negative log likelihood, which basically converts these scores into probabilities and gives me the negative log likelihood of the data, which I will define precisely next week. Yes?
Yeah, I was going to ask about that. Can this score be
Right. So normally these scores are, since I don't have any control over W, these scores are arbitrary real numbers, right? So I'm going to do some magic to turn them into numbers between 0 and 1 that represent probabilities. And then I'm going to define my loss function in terms of the negative log probability that was assigned to the correct answer. And I'm going to try to minimize that, which means maximize the probability of the correct answer. That's what the NLL stuff does. Okay, so after that setup, let's initialize our model. Here's our original loss, 2.83. Now this is a log probability. Actually, this is a, what is this? This is a negative log probability that I'm trying to minimize. This is the average probability, average log probability I'm assigning to the correct answer. Can anybody guess why this is 2.83? What's special about the number 2.83? So normally if I'm trying to, starting with a random model, you would expect each of these numbers to be similar to each other, right? You wouldn't expect the correct answer to be a lot bigger than the incorrect answers, right? And if I convert these things into probabilities, basically a random model is going to assign 1 over 10, roughly, to each answer, including the correct answer. And what is the logarithm of 1 over 10? Does anybody know?
Minus
2.83. Well, yeah, in natural logarithm, sorry. So that's where the 2.83 comes from. It's basically the minus log of 1 over 10, which is what my random model is assigning to these correct answers right now. And if my model after training becomes so good that it assigns probability 1 to every correct answer, what is my loss going to be? 0, right? So minus log of 1 is still 0. So the goal is to drive this number down to 0 in my training. So I can also look at the average loss for the whole test set. I can also calculate the accuracy for the whole test set. Loss and accuracy are different. Again, loss in this particular case is the negative log likelihood of the correct answers, whereas accuracy is how many of these things did I get correctly, right? So out of these 10,000 examples, I got 0.04 of them correctly. I wasn't particularly lucky. I mean, if I flipped a coin, I would expect to get 10% correctly, but I'm at 5% right now. But starting at a random initial position, I shouldn't be too upset. So let's train this. That's going to take apparently about 17 seconds. So you have 17 seconds to ask me questions. This is running on a GPU machine, by the way. It's running on a K80 GPU, because if I run this on my laptop, I couldn't finish the whole thing during this class. So that's why you need to go sign up in the, for these Amazon machines. Okay, well, 27 seconds, because my PhD students are keeping the machine busy right now, I guess. So I ran this, how many epochs? 60 epochs I ran this by. Let's calculate the loss for the training set and the test set. That's another 15 seconds, and I'm going to flop that. Okay, so let's see the whole thing. Okay, so I trained this thing for 60 epochs, which means I went through the whole data set 60 times. Each time I used the data set split up into 600 groups of 100, right? And I calculated my gradients and stepped in the opposite direction in the W space, and the losses came down. Now I plotted the loss for the training set and the test set differently with different colors. So blue is my loss on the training set, and red is my loss on the test set. Training set is the thing that I see and I calculate my gradients by. Test set is the part of the data that I haven't seen while I'm training the model. That distinction is important because, as you see here, my training set loss is low, which is good. Okay. However, it's not a good estimate of my performance because when I give it never before seen data, its loss is higher. Okay, which means it's not doing as good in the examples that it hasn't seen before, which is not very surprising. And this is called overfitting. And one of the first things to learn in machine learning is basically to be honest about overfitting and always keep your test set separate from the training set and never use it during training, so you can actually have an accurate estimation of how well this thing is going to do on never before seen data. So that was the loss. By the way, the loss started at 2.3 and it came down to 0.25-ish. Right, so it did come down a lot. I don't know what probability that corresponds to, but this is the plot of the accuracy. This is easier to understand, or error. So these are the percentage of instances that we got wrong. Okay? So in 60 epochs, in the training set, we come down to almost 7% error rate. So that means we're basically getting 93% of these instances correct. Whereas the test set error is closer to 8%. So that we're not doing as good on the test set. Okay? All right. So that was basically the very early history. So here is what these guys looked like back in the day. They were built out of little, well, they didn't have computers in 1958 that were really usable. So they actually built these things electronically. And here you can see Rosenblatt, the guy who first invented the first training algorithm for perceptrons, which is actually different from the algorithm that we used, trying to train it to recognize the letter C, which is a similar problem. It's just letters instead of numbers. Big TV camera, lots of wires representing the weights and connections. But he was able to show that this thing can be trained to recognize simple letters. And this is the perceptron algorithm. I'm not going to dwell too much on this. One of the earliest results, theoretical results in machine learning, is the perceptron convergence theorem, which basically says if there's a set of weights that can solve this task perfectly, then this learning algorithm will find it. Okay? So, so that was good news. However, about 10 years later, Minsky and Pepper, two AI math wizards, wrote this book called Perceptrons, basically detailing all the things that the perceptrons could not solve. Okay? So it turns out that a single neuron, a single artificial neuron, can only learn a certain set of concepts, but it can't learn all concepts. The reason is, I don't have the reason here. I don't have the reason here. The reason is it's a linear function. Okay, since it's a linear function, it can only learn things in X space. Let's say this is X1, this is X2, and here are some positive examples, and here's some negative examples. It can only learn things that basically have a linear decision boundary in the X space. Okay? If there is some pluses over here and some minuses over here, and the learning, the curve is kind of complicated, I don't know, if this is your decision curve, okay, everything inside this curve is plus, everything outside is minus or whatever, the perceptron can't learn that. Okay? So it has fundamental limitations, and most of the problems you're going to see do not fall nicely into the linear solution box. So, well, however, this criticism only applies to a single perceptron, which is a model of a single neuron. Everybody knows that our brain has, 100 billion neurons, so obviously that criticism is not valid if we can actually create a network of these neurons and train the whole thing, right? The problem is between 1960 and 1980, people did not know how to train multi-layer perceptrons, basically a bunch of these artificial neurons connected together. Right? You not only need to have the architecture, you also need to have a training algorithm so that this architecture can learn whatever you're trying to teach it from examples. And the perceptron algorithm only worked for single perceptrons. It didn't work for these multi-layer perceptrons. Until late 1980s, when I actually started my undergrad. People, actually like 3-4 people co-discovered this thing called backpropagation algorithm that could be used to train these multi-layer perceptrons. They published this book, which became very famous and revolutionized cognitive science. So if you take the cognitive science class, you can see them talking about connectionist models, which is the same thing as these things. Okay, so what do these networks look like? Well, basically, let's say I have 3 inputs. These are my x's. And I have 2 classes instead of the 10 over there, right? So what I do is I basically add a bunch of hidden units in the middle. And I create a network. And the hidden units basically take input from all the inputs and send their output to all the outputs. This is not the only possible architecture. It's one possible architecture called the multi-layer perceptron. There can be more than one hidden layer, okay, which turns out that theoretically doesn't improve the types of functions that we can represent. But yeah, so this is it. So instead of having a single neuron make the decision, you have a collection of neurons, each of which are calculating something presumably different, and as a whole, they're trying to make this decision. Okay? Okay. So, what does that correspond to in our matrix picture here? Basically, from X, I get a bunch of numbers here, and then I also have another W here, W1, W2, which multiplies this, and it gets a whole bunch of other numbers, and I may have more W's down below that get. So basically, more matrix multiplications, and in between each matrix multiplication, I have to have a nonlinear element-wise function. Otherwise, it doesn't work, because if you actually compose together a bunch of linear functions, what you have at the end is still a linear function. It can be represented by a single matrix. But if you actually inject some nonlinearities in between, then you get the power of being able to represent any, approximate any function you can think of. Now, and these are the different nonlinear transformations people have tried in history, and basically all of them work. Some of them work slightly better than others, but this picture is to show you that the activation function you use does not really matter all that much in terms of being able to solve different problems. We're going to be using this one most of the time. It's very simple to compute, fast, and it actually performs well. It's called ReLU, Rectified Linear Unit, which basically takes the output of each matrix multiplication and maps all negative numbers here to 0 and leaves all positive numbers alone. That's it. Okay? So if you just do that, it turns out That's sufficient to get good results. And we'll talk about the backpropagation algorithm, about how to train this. It's basically taking the gradients and moving in the direction of the negative gradient. And the important mathematical theorem people proved about these guys is the universal function approximator theorem. Basically, somebody proved that if you have enough hidden units in the middle of such a network, it can approximate any function you want. Okay? So it doesn't have the restrictions that the original perceptrons had, which is, things have to be linearly separable, otherwise it wouldn't learn, etc. When you have a network with enough units in the middle, it can approximate any function. That does not mean you can train it and find this particular setting of the weights that solves your problem, but at least in theory it exists, and it exists with enough hidden units. So, just to see the power of this idea, let's run it. Let's clean up stuff. Now, since I have more than one weight matrix for all of these different layers, I need to change my predict function. Remember, my predict function was W1 times X plus W2. Now, I actually have a more complicated predict function where the W weight becomes something like, weight 1, bias 1, weight 2, bias 2, weight 3, bias 3, however many layers I need. Okay? And what this predict function does is takes the components of W2 at a time and calculates Wi times X plus Wi plus 1 and applies this ReLU function I was talking about. This max 0x actually applies that function and returns it. Okay? I'm going to have you ask questions during the training, which is going to take a little more time this time. So define the loss. Actually, we don't redefine the loss. The loss is still the same. Look at the probabilities of the correct answers type of loss, the negative log likelihood loss. Let's train this. Okay, so that's going to take some seconds. You guys can ask me questions now. Yeah.
What about the differential at 0 in ReLU function?
So it turns out that it turns out for ReLU it's not a problem. I will, when we actually talk about this more, ask me again. But it turns out this is not a problem. The original activation function everybody used was a step function, which basically said if your sum is negative, then don't output anything, or output -1. If your sum is positive, output +1. And this was the reason why multi-layer neural networks could not be trained for a long time, because it didn't have derivatives anywhere, right? So here the derivative is 0, so you don't know which direction to go. Here the derivative is 0, you don't know which direction to go. And as long as, here the derivative is undefined, but that doesn't even matter because basically when you look at your gradients, the gradients are always 0, right? So from here, people first actually invented this, the S function, the tan H or the sigmoid. And this was supposed to imitate this one, but at least have derivatives everywhere. So now, basically if you are here and if you want to increase your input, you knew what to do with your weights, right? So if you're here and if you want to increase your input, you don't know what to do with your weights because the function is flat. Now, in the case of ReLU, if you're in this region, you have a clear derivative. If you're in this region, your neuron is dead, it's not doing anything, and the derivative is 0, so its weights aren't going to change. In fact, this is a problem with sometimes in some models with ReLU because some of your neurons get into this range and they just die. They're not being used by the model and they're not getting updated because the derivatives are always 0. As long as your non-differentiabilities are limited to just 1 or 2 points, it's not a big deal.
Does the algorithm gives error? It's not
No. Why? No. you just, I don't know how I did in Kenneth, but I basically either, well, the derivative here is 1, right? The derivative here is 0. So call this point 1 or 0. It doesn't matter which. Right? So as long as you don't give an error in the program, then everything works out. Okay.
Like it doesn't update these.
Yeah. Yeah. When you're at exactly that point. Yes.
Do people try to decide the activation functions according to something, or are they the things that learn?
There is some theory behind it, but most people decide based on the current fashion. And the current fashion is relative. Okay. It used to be sigmoid when I took my first neural network class. Now it's relative because it does better and it's cheaper.
Did I understand incorrectly? Does the number of hidden layers not matter, or?
So that's a good question. So if you have a single hidden layer, that's sufficient for the universal approximation theorem. So the universal approximation theorem says if the number of hidden units is sufficiently large, you should be able to approximate any function. But for some problem types, that number gets really, really large, exponentially large in the number of inputs, in fact. So even though the theory is true, it's not practical. Okay? So it turns out for those functions, having more layers allow you to achieve universality with fewer units. Okay? So basically having a deeper network allows you to learn certain functions with fewer units, which means fewer weights, which means you can learn from fewer examples and better generalize, right? So if you have a zillion weights in your model, and if you only have 1,000 examples, you're probably going to overfit and memorize these examples, and you're not going to learn anything useful. So it's always useful to have a smaller model with fewer weights, and having more depth allows you to do that. So we trained our MLP, and here's the results. For comparison, these are the previous results we had. Remember the loss was 0.29 something? So this was from the linear function we trained before, and this is from the multi-layer perceptron. So the loss came quite a bit down. The difference between training set and test set performance is more significant here, so there is more overfitting. We're memorizing the training set a bit more. Now let's look at the errors. Okay, so this is again comparing the errors of the linear model, which was about 7–8%, remember? And errors of the MLP, multi-layer perceptron. Notice that the training set is almost at 0 error. In fact, if I train it long enough, it does get to 0 error. But that does not mean it is perfect, because the test error is still about 3% or something. Okay, so that means with MLPs, I can memorize this whole data. I can basically give the correct answer to all 60,000 training examples. I can find the ways to do that, but those ways do not necessarily solve the problem with the test set, which remain at about 97–98% accuracy. So to move beyond that, we need to do what we were discussing earlier. We need to add more layers or find other ways to decrease the number of weights so that we can learn from these 60,000 examples enough to generalize to the test set, right? So in this case, I said the MLP is universal, but that has 2 caveats, right? So one, it's universal if I have enough number of hidden units, and it's universal if I have enough examples to learn the correct settings of those hidden units, right? So in this case, I used 64 hidden units, maybe it was too little, and I only had 60,000 training examples, which was not enough to generalize correctly. So since I can't change my data, I'm going to change my model, and see if I can come up with a model architecture that actually uses fewer connections, thus fewer weights. So let's go back to our presentation. And that brings us to convolutional neural networks, which are the sort of state-of-the-art neural network architectures that are for processing images. So the convolutional nets basically got their inspiration from the human visual system. In the human visual system, when people actually stuck some electrodes into cat brains, they realized that the ganglions, the retina itself has a bunch of different types of cells. One of these cells that integrate information is called the ganglion cells. And when they measured the receptive fields of these ganglion cells, receptive field means you have an electrode pointing to the cell, and then you show various things in the visual field, and then you basically ask, when does this neuron go off, right? So which kind of stimuli actually excites this neuron? So when you do that, they basically discovered in the 1950s there's these on-center cells and off-center cells, which have this type of shape. So off-center cells, they each have a particular location in the image they're looking at. And if it's an on-center cell, they get excited if there is something, a bright dot in the middle of that location. And if it's an off-center, it's just the opposite. The bright dot in the middle actually turns them off, whereas some halo around it turns them on. It turns out these are the exact filters that you need to take derivatives and find edges and do all sorts of nice things. After the ganglion, the signals move back to the brain, the cortex, the visual cortex at the back of your head. And they had electrodes in that region as well, and they were trying to figure out what these neurons responded to. This is Hubel and Wiesel, which I think got the Nobel Prize from this. And for a long time, they couldn't. They couldn't find a consistent stimuli that excites the cell they were looking at. And they were using a old-fashioned slide projector. And when they moved the slide off the projector, suddenly the neuron went like a machine gun. And they did it again. And then finally they realized that it was actually not sensitive to any shape or dot. It was sensitive to an edge. So when they were moving the edge of the page across the screen, that's when the thing got excited and started firing. So now this does not look like the fully connected MLP model that we basically discussed here and used. First of all, everything in layer 1 is connected to everything in the input layer, right? So obviously, in the ganglion cells or the visual cortex cells, this is not the case. Each cell in the middle only sees a particular region of the input. It's not connected to the whole input. So that's one difference. The second difference is each of these units in these hidden layers are free to compute any function they want. Their weights are totally independent of each other. So one can learn something totally different from all the other ones. Whereas in the visual system, we see that there is all these groups of cells, all of which compute the same function, but for different regions in the input. Okay? So remember those two ideas. Those are the two ideas that underlie this architecture called the convolutional neural network. So one idea is limited receptive field, only look at a particular part of the input. And the second idea is have a family of units that all compute the same function, but for different locations. When you put those two ideas together, you get something like this. First, you have sparse connectivity. So if this is the input layer or some layer m-1, this guy looks at only the 3 on the left. This guy looks at the 3 in the middle. This guy looks at the 3 on the right. Okay, instead of everybody looking at all the connections. And the other difference is all of these layer M units compute the same function. They have the same weights with their respective inputs. So those two ideas make up convolutional neural nets, and they recognize images well. And, we're going to talk a lot about them. And it turns out when you train them on real images, the types of filters they learn look very much like the types of filters your neurons have in your visual field. That was also exciting. But before we run out of time, I want to see if I can train one.
Hocam, this is the third wave you were talking about, right? Third wave of AI. At the beginning.
Yes, I guess perceptrons is the first, the multi-layer perceptrons and how to train them in the second. And these new architectures, the CNNs and RNNs, maybe I'll mention later, that are deeper, that are more difficult to train, they're the third. The third wave started roughly around 2012, where a convolutional neural net built by one of Jeff Hinton's students actually scored really well in an international competition of image recognition. So, and I want to just train something similar to that to recognize these digits. While this guy is doing what it's doing, which is going to take a few minutes, we can talk more. So, let's see. I have the I think I have it over here. Yeah, this is the ImageNet competition I was talking about for 2012, and you're basically given an image and you're supposed to recognize the objects in the image. There's about 1 million training images. There's about 1,000 categories for you to recognize, and each of these things have been hand labeled by humans to say what type of object is in each one. And basically, by using these convolutional neural networks, they significantly outperformed all the other competitors who were using the last 50 years of computer vision research. So then they threw out the last 50 years of computer vision research and everybody started using convolutional neural networks. And that's still going on right now. And it's going to take a bit longer. So. In the meantime, why don't we distribute the self-assessment quiz while we're waiting for this to train. Again, these are not going to affect your grades, it's just for us, for both you and me, to know where everybody is in terms of background. We're missing two. Okay, we'll put the questions online, and whoever doesn't have them right now, you can solve them at home and send the answers to me. Only 13 people were signed up for the class, so we we thought that printing 25 was okay. But so how many people are actually taking this class for grade? So definitely more than 13. Okay. And how many people are auditing? Okay, quite a few. Okay. And do you guys have any preferences on what time on Friday the lab should be? I mean, we may not get to choose because it depends on which classes are empty, but if I do get a few different time slots from the registrar, I'll email you and you can tell me your preference. But for that to work, you should all sign up in the mailing list if you're not there already. Don't forget to write your names. In fact, let's take a name attendance so we know who's.
Hocam derslerin karşılığını aldım. Başka okuldan almışsak falan boş.
If you don't know the answer, leave it up to you, of course. That's the whole point of the quiz, right? To figure out what you do know right now. No cheating on Google. In the meantime, when you're done, the experiment with the convolutional net has finished, and the lowest these two lowest lines are for the convolutional network. The middle two are for the multilayer perceptron, and the top two are for the linear model.
What about those bump over there?
These bumps?
Yeah.
Yeah, the learning rate was probably too high for that. So sometimes when your learning rate is too much, the training error can go up and down. If we make the learning rate smaller, it will go smoother, but it might take longer. But the convolutional net definitely gets to almost zero loss in about 20 epochs, which is impressive compared to everything else. And also, it's even though there is overfitting, it does get 99% plus accuracy. This is the loss one. Let me show the accuracy one too. Yeah, this is the error, percent error graph. It's doing definitely better than 99%. You can try to run this notebook on your laptops. It will take longer. Once you have the access to the Amazon machines or HPC, you can learn how to set the notebook stuff up from the TAs and run this yourself with the code. To-do list for everyone. Okay, our time is up. Are there any questions?
Things which do not generalize, more and more simply eliminate for test.
For which one?
For all of them, I mean,
so remember that these are percentage error rates, and these are not the numbers that our training hypothesis are plan loss. So when you're optimizing loss, what you're doing for the training set is that you basically have already after a while you have to decide all your necessary increasing the probability of so what that means is that you know the more you train the accuracy that depends on what that works. But basically your goal is
attendance sheet'i de imzalayın.
Ya bak üniversitede
önemli değil canım, önemli olan şu konularda bilgin var mı yok mu? İmza mı?
Hocam ders bilgileri.
O registrar biliyor onu. Bu sınıfta kimsenin okuması ama ne kadar kızma var ama isteyen istediği.
Öteki üniversite.
Hoca almam mı diyecek?
Gel.
Mail listesine gitmekten ya ben dersi kayıt almak istedim. Size gitmenizi takip etmek istiyorum. Yani geleceğim zaten buraya.
Size sorun.
Sadece örnek yani.
Tamam, ben o zaman size gönderirim. Onayınızı.
Postmayalım Instagram'a.
Mail.
İki tane fikir var. Bir tanesi lokal İkincisi şehirde olması. Eminim vardır insanlarda yapılmış deneyler ama ben
PD'yi alıyoruz ama zorundaymışım zaten.
Trial bir şey veriyor.
sana sordum değil mi? Sana geldi.
Bilmiyorum ya.
Nasıl geldi? Bir şey de alacağım ya. Ya çünkü yok.
Almaz sistemi değiştirdik ki. Yani keşke midterm de alsın. Midterm var.
Ben Temmuz 15'e istedim.
Bari buradan çıkıyor.
Tamam iyi ya.
Şurada bir evaluation var.
Şey sözünde yapar.